In order to understand spanning tree, we have to remember how switches learn layer 2 addresses in forward traffic. If you remember, as an address arrives at a switch port for a destination that the switch doesn't know about, it takes that frame and forwards it out all of its ports. If you happen to get a loop will cause a broadcast storm and could possibly take the network down. It's fun to watch in a lab, but if it's in production, it's not fun for your users or your career. Most unmanaged switches do not run the spanning tree protocol, which is why it's important to have managed switches in your environment. We need spanning tree to allow for redundant topologies in our network environments. So let's take a look at what we just talked about. Here I've got a network that's redundantly connected, and if this host sends out a frame for an unknown destination, switch 1 will forward that frame out both ports. Switch 2 now receives that frame and will forward it out both ports. Switch 3 receives that frame for an unknown destination and forwards it out both ports. And here's where the fun starts. Switch 4 receives that frame from both sides and will forward that twice out this way, once over here, and we'll forward it out multiple ports. And around we go as the traffic keeps replicating and multiplying throughout your network. It gets to the point that there's so many packets coming in and out of the switch that it can't process all the information. It drives up the CPU utilization. It can cause something called MAC address table thrashing, and it can bring your network to its knees. We need the spanning tree protocol for loop prevention for layer 2 networks in Ethernet. In redundant topologies, it puts redundant paths into a blocking state and prevents loops in the situation we just talked about. It builds a layer 2 topology tree with a single root. The root bridge placement is very important. You want to make sure it's in the center of your network on a switch that has plenty of horsepower. The reason we want it in the center is we want to keep the diameter of our network as small as possible in order to limit the size of the spanning tree calculation that it has to do in the case of a reconvergence. Over time, there have been several different types of the spanning tree protocol. We started with 802.1d, which was an IEEE standard, and from there went to CST, or Common Spanning Tree, where we had one instance of the spanning tree topology for all the VLANs. Cisco improved on that with per VLAN spanning tree and per VLAN spanning tree plus. Per VLAN spanning tree had one instance of spanning tree per VLAN, allowing you to be able to load balance and reduce the amount of fate sharing in your spanning tree environment. The downfall to it was that it used the ISL trunking protocol, or a Cisco proprietary trunking protocol. PVST Plus was the same as PVST, but instead used 802.1q for trunking instead of using the Cisco proprietary protocol. Since then, they've improved on the standards-based protocol by releasing Rapid Spanning Tree, or 802.1w. It's an IEEE standard, an advanced version of 802.1d. Has faster timers and faster convergence after a topology change, and has the equivalent features of Cisco's Port Fast, Uplink Fast, and Backbone Fast. Multiple Instance Spanning Tree is similar to PVST, but instead of having a separate spanning tree instance for each VLAN, we can actually group multiple VLANs into a single spanning tree instance, which allows for higher scalability for larger networks. There's also one more improvement. There's Rapid Per VLAN Spanning Tree Plus. Rapid VLAN Spanning Tree Plus is supported on the Nexus device with multiple instance spanning tree. Rapid Per VLAN Spanning Tree Plus shares all the same features of Rapid Spanning Tree, but allows you to have multiple instances of spanning tree per VLAN. Here are some examples of loops in redundant topologies, and what spanning tree would do to resolve those loops. first it would elect a root bridge, and then by considering port cost, it would choose to disable links in order to provide a loop-free topology. Spanning tree works because switches send BPDUs, or Bridge Protocol Data Units, to each other. There's three types of BPDUs. There's an inferior BPDU from a lesser bridge, a superior BPDU from a greater bridge, or a topology change notification letting you know that something has happened on the network. In a spanning tree environment, there is always an election for a root bridge. The bridge that's going to win the election has the lowest bridge ID, and the bridge ID is a combination of bridge priority and lowest MAC address. By default, all bridge priorities are 32.768. So by default, the lowest MAC address will win. It's very important to be very deterministic on which switches are your root bridges in your environment. We want to pick switches with high horsepower that are in the center of your network. That way we decrease the diameter of the network and allow the most optimal path to the root, as well as the smallest diameter of network. Now back to the lowest MAC address. It's quite possible that you could have a very old switch on your network with the lowest MAC address, which is why it's very important to make sure that we set the priority and know which switches are going to be the root, because what we don't want is a very small switch with low horsepower being the root of our network. It's also important to remember that topology changes trigger new BPDUs, and depending upon which links fail, could possibly trigger a new election in your environment. By default, Spanning Tree has 5 different states that ports go through as they are trying to find loops in the network. In older Spanning Tree protocols, these states were disabled, blocking, listening, learning, and forwarding, and each state had a time associated with it. So as you can see, if you add 20 to 15 to 15, you could wait over 50 seconds after a link failure before you start forwarding traffic. With Rapid Spanning Tree, we greatly lessen the number of states a port has to go through in order to become active, and we go right from discarding to learning to forwarding. As you can see, Rapid Spanning Tree greatly reduces the amount of time it takes for a port to become active. Finally, let's take a look at how Spanning Tree finds its path back to the root. So let's assume switch 1 is our root bridge. A root bridge does not have any root ports, it only has designated ports because it is the bridge. So it's going to have 2 designated ports. Now switch 3 and switch 2 are going to elect their root ports, which will be the ones with the lowest cost back to the root bridge. In this case, that would be these ports. They will now determine which port is their designated port, which once again has the best path back to the root bridge. Now depending upon the type of BPDUs switch 4 is receiving, there could be a better path than the other. In this case, most likely it's going to receive superior BPDUs from both directions, and it's going to have to make a choice on which port to make the root port. In this case, it's going to choose the higher numbered port and make this the root port and block this port. Please spend some time reviewing the types of spanning tree that are available, the types of spanning tree that are supported on the Network Nexus product, which would be rapid spanning tree and multiple instance spanning tree. It's also very important that you know the different states that ports go through, how they elect their port types, and how they elect the root bridge. Please join me in my next lesson, Understanding MST.